Alrighty, so I have here in front of me a molecular modeling kit. This is Dr. Kaiser, and I am going to walk you through how we can use molecular models to understand the VSEPR shapes of the first 8 molecules for experiment 10. The first one that we did was carbon disulfide. And the way that we would draw the Lewis structure for that one is we would have the carbon in the center. And we would have a sulfur on either side. And then the sulfurs would each have a lone pair. So we have full octets on each atom. But the way that we represent that with this molecular modeling kit is the central atom is the carbon here, and then we have a double bond on one side, and we have a double bond on the other side. So this is our central atom, this is a sulfur, and this is the other sulfur atom. And if we look at the bond angle here, this is a 180-degree bond angle, and we call the name of this shape linear. So moving on to the next molecule that we did the phosphorus pentachloride. For that one, we put the central atom phosphorus in the middle, and we put the chlorines around it like so, and each chlorine had to have a full octet. If you missed the video where we drew the Lewis structures, you can check that out. Now, if we draw the molecular, or we create the molecular model for this substance, the central atom is represented by this pink sphere, and then the bonded chlorines are represented in green. And we have what are called axial positions. So the red bonds going up and down from the central atom, these are your axial positions. And then the gray bars are your equatorial positions. And so you can spin this like a globe, and the 3 chlorines go around the equator. That's why they're called equatorial. And if you'll notice the bond angle between the chlorine at the bottom, the phosphorus in the middle, and the chlorine at the top, that's a 180-degree bond angle between the 2 axial positions. But if we turn it this way, the bond angle between the equatorial positions is 120 degrees. So this one here, 1, 2, 3, 1, 2, 3. That is a 120-degree bond angle. And then we also have a 90-degree bond angle if we put this chlorine bond in the plane, chlorine phosphorus bond. The bond angle here is 90 degrees. So there's 3 different bonds in the shape, and this shape is called trigonal bipyramidal. My son has these really cool Magnatiles that you can use to make the structure of the face. So the trigonal bipyramidal shape is actually a triangular base and 2 pyramids, something like this. So if you look from the top down, That's kind of like this view here. So you have, yeah, kind of like this. So this shape could actually fit inside of this magnetile structure. If we turn it like this, you can see that there's one point sticking straight up in both. And one, the axial positions are these two here. And then we can turn it on its axis like this. So this is called trigonal bipyramidal because you have a pyramid on top and you have a pyramid on bottom with a trigonal base. So this blue magnetile in the middle here is the triangular base. And then these other pyramids are, it's called bipyramidal because you have one pyramid coming up and one pyramid coming down. So let's go to the next molecule. We had our sulfur hexafluoride. And if we were going to draw the Lewis structure, it's not too exciting. You'd have to watch the other video for how this is done, but this gives you a structure, at least of the central sulfur atom and 6 fluorines bonded to it. So I'm showing this is like your central atom, and then the fluorines are in white, even though we normally reserve white for hydrogen. And the name of this shape is called octahedral. So we can also use the magnetiles to create an octahedral shape. Okay, so here we have side by side the molecule and a representation of the three-dimensional sphere, or you can imagine that this pink and white model could fit inside of this magnetile model. You have 2 points coming out at you, so these two are coming out at you. So that would be these two coming out at you here. And then you have 2 fluorines going away from you. That would be these 2 points back here. And then you have one coming up and one going down. Those would be like these two right here. And you can spin the model around like this. The idea here is that it's called octahedral because if you enclose the model in faces, you would have 1, 2, 3, 4, 5, 6, 7, 8 faces. And that's why the name of the shape is octahedral. And using the model like this, you can kind of understand that all of these points are equivalent and all the bond angles are equivalent. So you can turn this shape any way you like, and each group is still 90 degrees from every other group. So this is kind of the hallmark of your octahedral shape. Now, of the varieties of shapes that we have when you have a lone pair, we had one example of the sulfur tetrafluoride. So what that would look like is this group here. We had a central sulfur atom. And then we had a lone pair, and we had 4 bonded fluorine atoms. Okay, so this is 5 domains, and the lone pair would go on one of the equatorial positions. So the name of this shape is called seesaw, remembering that this is a lone pair now. And our molecular geometry is called seesaw because we have like a little teeter-totter formed by these fluorine atoms bonded to the central sulfur atom. If we look at it from the side, this is our lone pair up top here. And then we have the legs of the teeter-totter, and then we have the positions where the children would sit on the playground and play on this teeter-totter, okay, or seesaw. The next molecule that we had was sulfur dioxide. And it had a lone pair like on the central atom as well. And what we have here is trigonal planar. It's called planar because all three groups are in the same plane, which if you look at it from the side, you can see that it's flat. But if you look at it from the top down, you can see that this trigonal planar shape has a bond angle of 120 degrees. And this would be the site where the lone pair would be occupying. So you would call this either angular or bent, because here would be your oxygen, this would be your central sulfur, and then this would be your other oxygen. Okay, our next molecule that we drew was the nitrogen trichloride. We had a nitrogen in the middle. We had 3 chlorines. And then we had a lone pair on the central atom. So if we were going to make a 3-dimensional model of this, it would look a little something like this. So this would be like a top-down view. And the site where my hand is, this would be the lone pair. So the lone pair is occupying one of the sites on the tetrahedron, and then you have the chlorines bonded. And I know we normally reserve red for oxygen, but in this case, I'm using the red as the chlorine. And we normally reserve black for carbon, but I'm using this as the nitrogen. So the bond angles here are going to be slightly less than 109.5. The geometry, when you have 4 domains, is called, the electron geometry is called tetrahedral. But when you have a lone pair in one of the sites, the remaining groups form a trigonal pyramid. So we would call the name of the shape trigonal pyramidal, because you have the nitrogen kind of at the top of the pyramid, and then you have the 3 chlorines forming the bottom of the pyramid. Trigonal pyramidal. And we already looked at the trigonal bipyramidal with the Magnatile model. But this would be like just a single tetrahedron, and I only needed 4 Magnatiles to make this. I have 1, 2, 3 faces, and then 1 triangular bottom. So this would be like your trigonal pyramidal shape. Okay, the next one we had was the butane. I'm not sure this will even fit. I'm gonna have to back up the camera a little bit. So this is our molecular model for the C4H10. I'm not showing any of the hydrogens because I don't have enough of them. But what's interesting is this modeling kit shows how single bonds have free rotation around the bonds. Each of these bonds has free rotation. I can freely rotate all of these bonds. And so that's what's interesting about single bonds, is that they have free rotation. Any of these groups can rotate around. And in reality, this molecule would be kind of flopping all over the place. All the bonds would be rotating depending on the temperature. Remembering that kinetic energy in chemistry we think of as molecular motion. And so each of these vertices is a carbon atom, and at the terminus, all these termini are hydrogen atoms. And then last but not least, we can look at this same exact model for our chloroform, except in this case, we would have one hydrogen up top and 3 chlorines all around. So instead of a lone pair now, we actually have 4 bonded atoms. We have the less electronegative hydrogen up here and the more electronegative chlorines down here, and then the central atom would be the carbon. So we can see how this would be a polar molecule with the electron density where my hand is and a lack of electron density up here where the hydrogen is, because all 3 of these electronegative groups down here are electron withdrawing, leaving this hydrogen up here with less electron density even than normal. So this would be an example of a polar molecule. And that would be our CHCl3.